Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about what is called kinetic molecular theory. This is often abbreviated as KMT, kinetic molecular theory. I realized after we started going over Boyle's law today that typically I teach kinetic molecular theory first. And so I thought I would just backtrack since we're not too far into the gas law unit just yet. And we could talk a little bit about KMT. So before we jump into what is kinetic molecular theory, just a quick review on some gas stuff just in general. So sketch a particle diagram for any monatomic gas. I wanted to review this term monatomic. We spent a lot of time in the beginning of the year talking about diatomic gases. Monatomic, though, is going to mean made of one atom. And really, there's only one column on the periodic table that exists as monatomic gases because they are stable enough to exist as single atoms. And those, again, are our noble gases. So let's just pick any good old noble gas. So let's just say, I don't know, argon. Okay, and let's go ahead and sketch a particle diagram for what that would look like. Okay, so we have our gas particles. Remember that gases are going to take up the space of the container. They're going to have a good amount of space between those particles, and they are able to kind of expand and contract. So again, let's just quickly jot actually that information down so that it is in your notes. So again, gases have no definite shape, okay? No definite volume. Okay, they take the shape of the container, take volume and shape of container. Okay, and they are spread out. And something else I just wanted to make sure to add into our notes, and we talked a little bit about it in class today, which is the idea that gases are compressible, while solids and liquids are not. So why is it that gases are compressible, but solids and liquids are not compressible? And again, it has to do with all of this extra space that exists here in that particle diagram. So gases are compressible because there is lots of empty space between the particles. And if you think about it, they also, just as a reminder, if we bring this back to intermolecular forces, they have weak intermolecular forces or weak forces of attraction. And so because of that, they are spread out and we are allowed to kind of push them back into a smaller space. All right, so a little bit of a review of just gases in general, but now let's talk about what is kinetic molecular theory. It sounds kind of scary. It's really not scary at all. Kinetic molecular theory is simply just going to be a set of rules that help explain or predict the behavior of gases. So why is it that gases spread out? Why is it that gases take the shape or the volume of the container? Why is it that, since we've already talked a little bit about Boyle's law, why is it that when pressure decreases, volume increases? Okay, and again, let's just note that this sometimes goes by KMT for kinetic molecular theory. Now we're going to go through a series of 4 postulates. That's a fancy word for just saying a rule, right? We said this is a set of rules. So 4 rules or 4 postulates that help us explain the behavior of gases. So let's go ahead and jump to postulate number 1. Okay. So postulate number 1 is due to the large distance due to the large distance between particles, okay, the volume of the gas particles, the volume of the gas particles themselves is negligible. Okay, so a lot to kind of unpack here. So let's just start with that term negligible, right? What does that term negligible mean, right? So negligible means that they really doesn't have an impact, okay? That the gas particles themselves, even though they do occupy some space, it's not even worth talking about. The actually majority of the space is actually empty space, or there's nothing there. And to kind of demonstrate what we mean by that, I want to think about like, let's say a balloon, okay? So let's say that I have this balloon and I have my gas particles within this balloon, okay? Now, within this balloon, what causes a balloon to keep its shape? Well, a balloon keeps its shape by the collisions that exist between these different gas particles and the outside of the inside of the balloon. So when you have a balloon that's really big and intact, right, that balloon is actually kind of moldable sometimes. You can kind of like squeeze it down, you can force the gas into different places. And a lot of that is because that is empty space in there, and that the shape of that balloon is being kept because those gas particles are colliding with the inside. Now note from this picture that the majority of the space in this balloon actually isn't those 3 gas particles in there. It is mainly empty space. And so if we say that this balloon is 35 milliliters of gas, what this postulate is saying is that that 35 milliliters is primarily empty space and not actually the gas particles themselves. So they're saying that the gas particles are very, very teeny tiny compared to the overall size of the container. All right, excellent. Postulate number 2, moving ahead, okay? Sorry, postulate number 2 states, let me get this out of the way. Okay, postulate number 2 states that particles of gas have such weak intermolecular forces. Ooh, not what I meant to do there. Move myself out of the way for now. Okay, they have such weak intermolecular forces that the intermolecular forces, or the forces of attraction, are considered negligible. Okay, so essentially, we did talk about this a little bit in class, how the gas particles, or how particles that don't have dipole attractions or London dispersion forces still experience, dipole or hydrogen bonding, they still experience some London dispersion forces. However, what this postulate is stating is that any of those London dispersion forces felt by gases are so minimal that we are basically going to just say that they don't have any attractive forces, right? If gases had attractive forces, they wouldn't be gases. So gases have such weak intermolecular forces of attraction that they are considered negligible. There is no force of attraction. That one is kind of easy to understand, I think. All right, for this next one, we're going to talk a little bit about the motion of gas. And so I do want to go ahead and pull up just this quick little Java, what do we want to call this? Like a simulation. And so you'll notice here that we have an empty box right now. I don't have any gas particles in there. So let's go ahead and add some of these gas particles in and just kind of observe what their motion is. Now, what I would recommend for this is actually kind of taking one particle, if it's possible, and observing. I'm going to expand the size of my box here just so, and let some of these particles out, I think, so that we can kind of observe just 1 or 2 of these particles, and just kind of track their motion and see what they're doing here. So try to focus on one. What do you notice about its motion? How does it move? Okay. So the things that I want you to notice, and the things that we're going to jot down to kind of explain here, and this one doesn't do a great job of showing the speed at which gas particles move because it is a heavier species of gas. But gas particles, as I add the heat, obviously we see a increased average kinetic energy and increased movement. But notice that the gas particles themselves move in rapid motion, okay? None of the gas particles ever stop to a still. They do slow down here and there, and we'll talk a little bit about why that is in postulate number 4. But notice that they move in straight lines as well until they are colliding with another particle. So if you keep watching, that particle should move in a straight line until it collides with another particle. Okay, and so this is going to lead us to postulate number 3, which is going to state that particles or gas particles move in rapid, random, constant, lots of describing terms here, straight line motion. Okay. And that's going to take care of kind of describing how gas particles move. So now we've talked a little bit about size of gas particles, explaining the size of them. We've talked about explaining basically why they're gas particles, why they don't just attract to one another. We've talked now about how they move. And now our last postulate, before I jump in and kind of give you that postulate, we have to define what is called an elastic collision. So in order to do that, we do need to talk a little bit about, or like what I like to talk about is bumper cars. If you've never been on bumper cars, I'm sorry, you should go. They are so much fun. Maybe not when you're really little because you tend to get stuck in corners, but as you get older and you carry more mass, they actually are a lot more fun. So if you haven't been on one in a while, I do recommend. All right, so we have 2 bumper cars here, car A and car B. They're of equal mass, that's really important. Okay, both the people weigh the exact same amount, and they're traveling in the same direction as seen in our diagram. Okay, car A is going to collide with car B. So what happens to the speed? So our initial speed of car A is 10. Our initial speed of car B is 5. Okay, so what's going to happen to the speed of car A after the collision? Okay, well, if car A collides into car B, car A will slow down. Okay, what's going to happen to the speed of car B? Well, if car A slows down and car B is going to speed up. Okay, you may have experienced this in bumper cars where if somebody kind of collides with you, as long as you're not hitting into a wall, if they collide into you from behind, then it does push you forward. Okay, now why is that the case? Okay, that's the case because car A transfers its energy into car B. Now, in this collision, because they are of equal mass, because they are bumper cars and they're on that special kind of flooring and special kind of I don't know, electricity, right? A bumper car is kind of run off electricity. We are going to say essentially, right, that all of the energy from car A is transferred to car B, and we lose none of that energy in that collision. So our total momentum overall is going to stay the same, meaning that our initial kinetic energy, which totals 15, should theoretically stay approximately the same. So initial kinetic energy is equal to our final kinetic energy, okay? And this is an elastic collision. So an elastic collision, okay, is going to be a collision in which energy is transferred completely. And what do I mean by that? I mean there's no loss of energy. Okay, we lose no energy in this collision. And so this leads us to our 4th and final postulate. okay, our fourth and final postulate, which is going to state that, okay, all collisions, gas particles have are considered elastic. Okay, so all gas particles that, or all collisions that gas particles have are considered elastic. So anytime they collide with one another, energy is transferred to the other particle, no energy is lost. Anytime they collide with the wall, okay, energy is transferred to the wall, no energy is lost. Okay, so if all of these substances, if all gases truly followed the rules of KMT, or if all substances followed the rules of KMT, all substances would be gases. How do some substances deviate from these postulates? In which ways do you think that these postulates are not true? A lot of what we've already know, we can go back and kind of apply our knowledge to these postulates. So essentially, which of these postulates can we prove incorrect? Okay, so first and foremost, let's start with postulate 1. Okay, due to the large distance between the particles, the volume of gas particles are negligible. Now, in some cases, sure, gas particles are small, and overall, yes, we are talking about a submicroscopic scale, right? We're talking really teeny tiny, but to say that gas particles don't have volume is kind of an oversight, especially some of those larger gas particles. They do occupy space, they do have volume. So we are going to say that gases do have volume. Okay, let's go back and see about postulate 2. Now, again, postulate 2 stated particles of gas have weak intermolecular forces and therefore they are negligible. Again, yes, they do have minimal intermolecular forces, but to call them negligible would be an oversight. We do have gases that do have attractive forces. Okay, so gases do have attractive forces. Okay, and our last one that I think is really easy to kind of pinpoint and rule an issue with is collisions, right? Are all collisions elastic? If that was the case, theoretically, you know, we would have balloons that would stay inflated forever. So I would have to say that, you know, collisions, especially collisions with the walls of a container, do lose, there is a loss of energy, okay? So not all collisions are elastic, okay? So you might be thinking to yourself, well, Miss Seeley, why did you bother teaching me kinetic molecular theory, the rules that govern how a gas behaves, if you're going to sit there directly after telling me them and say they're incorrect, okay? I get that. It's kind of crazy. But kinetic molecular theory is what it is, right? It's a theory. And it does do a good job of describing and explaining behaviors of gases. But we typically say that kinetic molecular theory is used to describe what is called an ideal gas. And an ideal gas is a gas which follows all the rules of kinetic molecular theory. Okay, now again, we are oversimplifying things so that we have a set of rules to explain the governing of gases, to explain why they behave this way. But there's no such thing as an ideal gas. There isn't. There's no such thing as an ideal gas. And so what I want you to think about before class tomorrow are the 2 questions listed below. Okay, if there is no such thing as an ideal gas, which substance behaves most like an ideal gas, or which gases do you think behave most like an ideal gas and why? And 2, if we could manipulate conditions to have substances behave more like an ideal gas, what conditions would, or how would we manipulate those conditions? Under which conditions would they behave most like an ideal gas? All right, everybody, thank you so much for tuning in, and I will see you guys tomorrow.